Hi guys, I was in Amsterdam this weekend just walking to the Amsterdam sign to get a cheesy picture taken, and I noticed these benches behind me. I thought I had to stop and just do a bit of structural analysis on them. Now they look really interesting actually. They've got that very thin profile, it looks like it's been bent out of one sheet of metal, and it kind of looks like how you would model a portal frame. So maybe we can do a bit of that with our back analysis and see if we can understand how that works. You can also notice there's lots of holes in the section, and maybe that has a purpose as well. We can find out later. We're going to model the bench as a portal frame, which is basically this goal-shaped structure you see here. And we're doing this basically because when we incorporate the legs of the bench into our analysis as well, we get a relationship occurring between the seat and the legs, and it gives us basically a more realistic analysis, although it's a little bit harder to work things out. Now, what we've got at the supports are pin connections, so they're allowing rotation when we apply a force to them. And we're doing that because of the cross section of the bench itself, which is that very thin sheet metal, which isn't going to actually provide a lot of moment resistance. It might provide a bit, but when we come to model things, we want to make things as simple and easy to analyze as possible. So we're going to simplify it to pin connections, which is conservative, but it's not going to be too far off. Now you might be wondering why we've got vertical legs on this model, and when we looked at the bench it had those inclined legs. And those inclined legs serve a purpose because they do offer some resistance to lateral loads. If you have a lateral force acting on one side of the bench, it's going to be resisted in part by a horizontal component of force from one of the opposite legs. But we're just going to be dealing with vertical loads today, so for simplicity it will make our angles a bit easier. We can model it with a simple right angled frame, and it's going to give us similar results to what we'd expect in real life. So let's apply some loads. We start off by applying a uniformly distributed load along the seat of the bench, and that would be the self-weight of the seat or people sitting on it. And we can get a good idea of the bending behaviour just from looking at deflected shape, because if you add a uniformly distributed load to just a simple bench, what you get is a parabolic distribution of bending underneath the seat. But there's a difference which we can see from deflecting this bench, and that's that these corners maintain their right angles, which means they must be resisting some moment. So on top of that original form of bending moment, we're going to have a hogging moment generated at the corners, the ends, the supports of this beam. So there's going to be a hogging moment, and that will be superimposed on top of the sagging moment, the parabolic distribution, to get a slightly more complicated shape of bending moment diagram. We can also notice when we load this that because we've got pin supports here, they're allowing rotation, and what that means is there's going to be no moment generated. Instead of generating resistant moment, they're just going to be free to rotate. So we've got zero moments here, and we've got hogging moments here and here at the connections, and there's nothing interfering with how the moment's going to change in between. So we're going to have a triangular looking moment distribution going from the connection all the way down to the support, and that'll be actually caused by the horizontal reactions which will be resisting this outward thrust. You can kind of see intuitively that there's going to be a thrust pushing this outward. There's going to be a horizontal reaction resisting it, and that's going to generate this triangular moment shape. So that may have all sounded a bit confusing, but let's bring it together. Let's draw the full bending moment diagram. So we have these pin supports, one on either side, and here's our frame. And we had the hogging moments at the top, generated by the fixity, the rigidity of these connections at the corners, and then we superimposed our parabolic distribution on top of that, and then these come round the corners, the tension is still on the outside, and there's no moment here, so we get this triangular distribution down to the base. And that's our bending moment diagram for this portal frame model of the bench. Okay, to understand how this bench is going to work, we need to look at the composite behaviour of the seat of the bench and the back of the bench working together. And the key to understanding this is actually to look at the depth of this section, which is a lot bigger when you combine the two. We're going to look at the moment of inertia, which is maybe for some of your new concept, but basically what it means is it's a number which indicates an object's resistance to rotation. And the resistance to rotation of any object obviously changes depending on how you want to rotate it. So if you want to rotate it around one plane, it might be easier to rotate than rotating it around a different plane. And that's a key concept. So we could define a plane about which this object is going to rotate. And for any given plane, it might be like this, it might be at an angle. We're going to have different moments of inertia. So this bench might have a certain moment of inertia rotating around the horizontal plane, and a different one rotating around the diagonal plane. But to fully define this plane, we also need to know the point at the plane that this line acts. But we don't know where that line is in the plane around which it rotates. So we need to find it. And the location of that line, which is called the neutral axis, is defined by taking moments of area around either side of the line, and where they're equal, that's where your neutral axis is. The moment of area will be the area of the section on one side of the line times by the lever arm, so the distance to the centre of mass around which that area acts. And if it's the same on the bottom as it is on the top, then that's your neutral axis, and that's where we calculate the moment of inertia from. If we found the neutral axis, we can work out the moment of inertia. The moment of inertia is basically dependent upon the amount of material we have in our cross section. So the bigger the cross section, the larger the moment of inertia, and from the distance of the material in that cross section away from the neutral axis. So in general, the deeper the section around that plane, the larger the moment of inertia will be as well. So if we kind of qualitatively compare the moments of inertia from this composite structure and from this section of the bench, which is just the seat without the back, we're going to see that in the case we've actually designed, the moment of inertia is a lot greater, and that's going to greatly increase the rotational resistance and therefore the bending resistance as well. So we'll draw on the neutral axis for this section, and it's going to go straight down the middle because the moments of area are going to be completely symmetrical on either side. And so if we take the area on either side, so let's take the bottom as well, just so it matches up with the other diagram, then we've got this area times by this lever arm, and you can see, but by having this section here, you've moved the neutral axis up considerably. So not only do you have a bigger area, but you've drastically increased that lever arm. And now, if we look at the area here times the lever arm to the centre of mass, you can see that lever arm is even larger. So not only have we increased the mass, we've increased this lever arm, and because the moment of inertia is dependent upon the distance away, this depth, then it's going to lead to a much greater moment of inertia.